Hello everyone, and welcome to another Verschijnen stream, high-dimensional probability. So last time we got to exercise 2.2.9, and I got a little stuck. So the ideas were sampling n copies of a random variable, and we want to estimate its mean. And my idea was that with some probability, a random variable has to be within some distance of its mean, if you know its variance, and that we could just like choose a distance around the mean that's large enough that all the variables with a union bound are like close to it, and then using that bound we can apply our bounded Hofting's inequality, because if you just like truncate them, you won't change the sum with high probability. But that turned out to like not be strong enough, because the bound we would need around the mean is proportional to root n, and then when you add up the n root n squareds, you get an n squared in the denominator and the numerator, and then you're not actually gaining anything as you increase the number of random variables. So that turned out to be pretty bad. But I realized, thinking about the problem more, that what we really need is actually a version of Hofting's for random variables of a given variance. It's actually kind of strange to me that like that wasn't an exercise, because it seems like a useful thing to do. Actually, probably maybe even more useful than bounded Hofting's. But I think I was able to work it out. So let me show you how it's done. So I guess our goal is okay. So what if I claim that? Yeah, I guess I should add some theorems and propositions. Let's see, where is everything? It's all in environment, or no, common environment. Right. So I should just new theorem. I'll call it claim. Okay, there we go. So the claim is let x be a random variable with mean 0 and standard deviation or variance sigma squared. Then what we want to show is that the exponential moment, the expectation of e to the xt, tx, is less than or equal to e to the variance squared t squared, and then the key is we get this factor of 2, so over 2. And let's see, I can just close this up. So if we can show this, then I think it should be clear that just from normal Hofting's inequality, that if you've got n copies of x, that just from the proof of Hofting's inequality, you can like get to here, but instead of like these a's, what you'll have is sigma squareds, and then you'll have n sigma squared, and then you won't have 2 copies of n, you won't have an n squared, and it'll all work out. So that's the idea. So how do we show this? So the way I showed it, there might be a better way, but I showed it in a similar way to how we bound just for Bernoulli random variables by looking at the generating function. I guess this is worth a proof. Okay. Okay, so we have the Taylor expansion of t to the x is of course equal to 1 plus tx plus tx squared over 2 factorial, so on. And now we take the expectation of this, and there's two cases, and I'll break it up into the two cases. So the two cases are that tx is greater than 1 and that tx is less than 1. So we just group the terms together, like the odd and the even ones, either with the subsequent one or the previous one, and bound the pair in terms of like just the even terms. And then we'll end up with just even terms, and then we will bound the coefficients we get by the coefficients of sigma squared t squared here. So let's see how that's done. So we take, and also importantly, this first term will vanish because the first term would not give us the bound we need. Okay. So I guess I'll write out the next term, or I'll write out the expectation. So the expectation of e to the tx is equal to, I guess, expectation of 1, which is 1, and then I'll skip the first term because we assumed it was mean 0. So tx squared over 2 factorial, I'll put brackets around that. And write another term, but with 3's. Okay, so that's the that's what we're trying to bound, and yeah, so this term vanished because of mean 0. Okay. And now let's bound the pairs of odd and even terms like I said we would. So there's two cases. So case 1, maybe I'll enumerate it. So case 1 is tx is less than or equal to 0. So what happens when tx is less than or equal to 0? What happens is you raise it to higher and higher powers, and it actually gets smaller, not larger. So in this case, we've got that tx, I'll just say to the I. So I'm going to look at, I guess, even I. So I don't think it's important for this first line. So we'll have tx to the I over I factorial plus tx to the I plus 1 over I plus 1 factorial. So this is going to be less than or equal to, so by assumption tx to the I plus 1 is actually even smaller than tx to the I. So I can just like upper bound this. So this is going to be less than, just copy paste it, so let's change the whole line, and then delete this. So what am I trying to do? I'm just making this I. Oh, and I think it just doesn't like that. What's the other problem? Did I not end the enumerate? No, I did. These extra lines are from. Less than or equal to, carets. Let me pull up the tech output. Let's say /item inserted $sign. Missing $sign inserted. Item case 1. Oh, right. Bullet is not a math mode command. Right. Or it's not a normal mode command. I have to put this in a... There we go. Okay, so case 1, we have tx is less than or equal to 0. And then... So what do I want to do next? I just want to... So these are just equal, so I'll just give these a common denominator, and you get I plus 2 over I plus 1 times tx to the I over I factorial. Yeah, I put the I plus 1 over there. And I'm going to need a line. Okay, so what did I do? I bound two adjacent terms by well, I almost bound it by the first even one. So this is like the even one exactly, and then it's slightly larger. There's I plus 1 over I plus 2 over I plus 1. And actually, this is why it's so important that this first term vanishes. This is why we need mean 0. Okay, but let's see what this gives us. So we've bound these subsequent terms, and let me also write down the Taylor expansion of this right-hand thing. I'll do it here. So note also that that e to the slash sigma squared t squared over 2 is equal to 1 plus sigma squared t squared plus I guess sigma squared t squared squared over 2 factorial plus dots okay. And now what? So the coefficient over 2. So I should have a over 2 there, and yeah, the over 2 is important, of course. Over 2, and then over 2 squared. But maybe I should put parentheses there. Okay, and now if we look at okay, I guess there's one more thing we need, which is Jensen's inequality, because of course this first term here, so we're looking at the expectation of tx squared, and this is exactly like t squared times the expectation of x squared, and because it's the mean 0 variable, that's just the second moment, that's just the variance. But for higher terms, it's not quite that, but we can like pool out the powers of 2. So maybe I should write that down too. So note, so the expectation of, I'll just say x to the say 2 times I is less than or equal to, so the important thing is I can pull out the I because, or can I? Wait, is that the opposite of true? So, okay, so raising to a power is a convex function, of course. Just picture the parabola. Or raising to an even power is a convex function. But raising to any power is convex for positive numbers. So that means that you do best by raising the tails to the higher power, so you want to be inside. So actually this should be greater than or equal to the expectation of x squared to the I, and this is just sigma squared, so sigma to the 2i. So let's hope this bound goes the right way. So does it go the right way? Hey, this is actually sort of concerning to me. I thought the bound was going to go the other way. But I think it should go this way. So I should say why this is true. So note by Jensen's inequality. Just double check, I guess. But I think it should go this way. Right, so yeah, I kind of wrote it like backwards, but the inequality goes the right way. Yeah, so you get a larger number if you do the convex function on the outside of the expectation, or a smaller one if you do it on the outside. And raising to an I is a convex function for positive random variables. I guess if it could be positive or negative, you have to be careful, of course. But x squared will be positive, so we should have this inequality. Now I'm a little confused because I thought this was actually going to work out, but this actually seems sort of backwards to me. So so this is what we're trying to get an upper bound on. So we want to show this expectation is less than this thing. So then I look at the Taylor expansion. The first term dies, but everything else stays the same. And then I like bound these consecutive terms to just get the even terms up to like this thing that's small for I greater than equal to 2. But now we have a problem. Yeah, I guess the problem is I've got like, so this is pre-expectation. I've got a t to the xi for I even, and I want to say that expectation of tx to the I is bounded by this, but it's not quite. Because it goes like the wrong way. Like here I've got the expectation of I. How am I going to bound it above by sigma? Yeah, and I guess this is like what I should expect, really, because I don't know. When you raise things to higher and higher powers, obviously like the tails are gonna matter more and more. So it should be a lower bound when you first take the expectation and then raise to a higher power, which is what we're seeing here. Okay. And I'm sort of stuck again, but I thought we should have this bound. So maybe there's a different way to go about it than the moment generating functions? Or maybe we need to assume more about x. But I really only want to assume that it has a mean and a variance, if I can help it. Yeah, maybe this is too much to hope. I guess this is, well, no, I was going to say it's sort of saying that x is sub-Gaussian, but it's not really saying that. Like, it's just saying that, well, it is sort of saying that in some way. Which is maybe false if all I know that it is that it has a variance. Or maybe true, actually. I think having a variance should be like actually a stronger property. No, definitely not. I'm getting everything backwards today. So what can I say? Maybe, like, should this be roughly true? I guess it like shouldn't even be roughly, like, it should equality roughly hold, but I guess like we shouldn't even have like rough equality. Like, I think like this could be arbitrarily larger than this if like x just has like a small, like you could imagine x that has like a smaller and smaller probability of being larger and larger, and then this is like the same for all those x. But this is just blowing up. So we shouldn't even have rough equality. This can be like arbitrarily larger than this. And this is exactly equal to this. Huh. Oh, there's a 3 coffee cupper. I wonder if this is even true. So we have this, and we have that, and this is what we're trying to upper bound it by. But how do we... Huh. I don't know. Maybe I should just move on. I thought I had it. I thought this like observation was the key, and I thought it followed from these kind of equalities. But we're so close, but this is just going the wrong way, and it's not even like roughly true. I don't think that it goes the other way, or that like these are comparable. Okay, I guess I'll just make a note for myself and move on. Let's do. Yeah, I guess I'll just move on to the next exercise. I guess so. If we had this, then we'd have Hoftings with like the denominator in the exponent being sigma squared n, and then it would just work out here because this would, instead of being an n squared, would be an n, and we could see that n being this large would be sufficient, and we wouldn't need like this stuff here. We would just have like straight Hoftings for random variables of variance. But it's not quite working out. Yeah, I wonder if there's some kind of like union bound where we can like say that like this is mostly true or something. I don't know. That seems like it wouldn't work out. Yeah. I guess these two approaches are just like totally orthogonal. We can't like stitch them together. Okay. Well, I'll think more about it. All right, let's move on to exercise 2.2.10. Okay, so small ball probabilities. So here we've got, again, our x1 to xn, and now non-negative independent random variables with continuous distributions. Assume that the densities of xi are uniformly bounded by 1. So we want to show that the moment generating function of xi satisfies that e to the exp minus txi is less than or equal to 1 over t for all t greater than 0. Oh wait, I wonder if that's the problem. I wonder if the sorry to jump back. I wonder if the problem is that we wanted a minus sign here. No, I guess not, because if we go back to where it was proven, heck, close. Where am I? I'm on the wrong page. Yeah, if we go back to where we established Hofting's, what was the idea? We had this e to the minus lambda t, and that's like our whole gain. It's coming from the expectation, and then this is the thing that we were bounding, and we got like no negative there. So like I want an analogous bound of this, where instead of knowing that xi is bounded or Bernoulli, I know instead that it has variance sigma. And I thought I could get one like this, but it didn't work out. Yeah, I don't know. It's strange because okay, and then let's just look at the next one. Okay, so I think morally this makes sense, because if xi has density bounded by 1, then like what's the peak case? The peak case is that xi looks like this, where it's like just at 1 until its total integral is 1, and then it's 0 then after. And if you graph this, then what happens when you compute this expectation? This expectation should be okay, so it's just smooth, so it should like be the integral of the density. So we just integrate from 0 to 1 of e to the tx dx, and this of course is just going to equal 1 over t e to the, or sorry, that should be a negative there. Should be, oh, so it should be negative 1 over t, wait, yeah, negative 1 over t e to the minus tx integrated from 0 to 1. And then, yeah, this is equal to 1 over t minus e, or minus 1 over t to the e to the t. Okay, so wait, do we get a slightly better bound than this, I suppose? For some reason I thought this would disappear and we literally just get 1 over t. But I guess that as t is, when t is large, this is like negligible. But I guess when t is small, this is actually very not negligible. I guess, does that make sense? Like if t is going, I don't know if that makes sense. Okay, so that's for this random variable, the uniform on the unit interval. Uniform on 0, 1. And so then I guess we need to argue that this has the largest moment generating function. Yeah, so intuitively that should be true. Yeah, that's definitely intuitively true. But how to make it precise? I don't know. Maybe I'll just say that for the problem. Okay, so this is 2.2.10. Okay, so the MGF of xi is maximized when xi is uniform on the unit interval. Maybe I'll just say if xi has probability mass anywhere else, we can reduce the MGF by shrinking it, but it can't be shrinked further than uniform on 0, 1 without increasing its density past 1. I guess it's shrunk. Sort of a hand-wavy argument, but it's essentially why. So in that case, we've got the expectation of the moment of the exponential minus tx is equal to the integral from 0 to 1 of the density e to the or the density, which is uniform, times the value, which is this, so x to the minus tx little x dx, which is equal to 1 over t e to the minus tx from 0 to 1, and that's equal to 1 over t. And then there is actually a little error, I guess. So minus 1 over t e to the t e to the t. Yeah, I don't think this goes away for any reason. Like, it's not like this is infinity. We're just integrating the density times the value. Okay, and this is less than or equal to, of course, 1 over t. Or should we be integrated from 0 to infinity and then we do lose this term? I don't think so, because like this should be multiplied by the density, which is 0 outside here. So I don't know. Okay, so deduce that for any epsilon greater than 0, we have the probability of the sum of xi being less than or equal to epsilon n is less than this very small thing. Okay. Oh, so this is just like redoing Hoffding's inequality. So what do we get? So we okay, we get epsilon here. So okay, so I guess I should do this in the next item. So we've got the probability of the sum from I equals 1 to n of xi being less than or equal to this. This should be, so we'll just redo the Hoffding's thing. So we'll multiply both sides by lambda and exponentiate them. So this should put a little delimiter there. So this will be the same thing. As this. And then just put some parentheses around. Right, so this is equal to this. And then by Markov's inequality, this should be less than okay, so or should this go a different way? Or no, this feels right. Okay, so the probability that this is like sort of backwards. Because I guess the like so Markov's gives a lower bound on the probability of being above the upper bound, and here we are kind of backwards. So if I just continue here, what would I do? I would take the expectation. This is like sort of backwards. Yeah, I guess there's a negative here. I think somehow I need to like incorporate this into my reasoning. I don't know if I want to like say, so the probability that this is less than this is the same as the probability that the negative of this is greater than the negative of that. And then oh, I think that is actually, what I want to do. I just add some negative signs. Oh, oops, wrong place to search. Just add negatives everywhere. Flip it around. And now it's looking more like a thing that we would apply Markovs to. So now we'll take the expectation of this and divide it by this. Okay, so then dividing it by this means the negative goes away, and we get e to the lambda epsilon n, and the expectation of the exponential of minus lambda times the sum of I equals 1, or I'll just say the sum to n of xi. Okay, now here's where we apply the previous part. So by independence, we split these up. For each of them, we get 1 over lambda. Right. So we get a... Okay, so this is less than or equal to e, or all places exp. So exp lambda epsilon n minus I guess like the exponential is like falling out here, so we just now are straight up dividing by t to the n. And by t I mean lambda, because I changed the letter. Oh, I misspelled my lambda here. Okay. Okay, I notice I'm getting my e to the n. I probably just want to choose like a different lambda. Yeah, I think I need to just choose my lambda more carefully. Well, maybe not. So yeah, I definitely want lambda in here. So this is sort of like, yeah, I guess the epsilon's ending up in like not the right place per se. Oh, I guess we choose lambda equals 1 over epsilon. Oh, okay. Okay, so yeah, if we choose lambda equals 1 over epsilon, these cancel and we get e to the n, and this becomes epsilon to the end. Okay, so we get exactly what we want, actually. Nice. Wow, that actually works out pretty well. So choosing lambda equals 1 over epsilon, we obtain I'll just say the desired bound. Or no, I'll just copy and paste the probability. That's better writing. Oh, I guess I didn't yank all the way. So it's less than or equal to exactly as desired, e epsilon to the n. Oh, I think I see the problem. I think this should be that kind of bracket. Nice. And that's I equals 1. Okay, nice. Okay, so we're done with section 2.2. Sort of. I guess I should go back and figure out how to like actually make a Hoftings with variance. I should probably just Google Hoftings with variance. I'm sure I'm not the first person to want this. And I guess I still need to write up my argument for this one, which involved, I think, some hand waving. I guess I just wrote it up on these pages, but didn't like work out the details. There might be errors. But yeah, for now, I think I'll move on to Chernov's inequality. I think that would be good. Oh yeah, also I might want to double check. Oh yeah, I guess this is a pretty sketch argument too. Maybe I should fill in the details there. Okay, but let's move on for now. So as we noted, Hoftings inequality is quite sharp for symmetric Bernoulli random variables, but the general form of Hoftings inequality is sometimes too conservative and does not give sharp results. This happens, for example, when xi are Bernoulli random variables with parameter pi so small that we expect Sn, the sum of n of them, to have approximately Poisson distribution according to Theorem 1.3.4. However, Hoftings inequality is not sensitive to the magnitudes of pi, and the Gaussian tail bound it gives is very far from the true Poisson tail. In this section, we study Chernov's inequality, which is sensitive to the magnitudes of pi. Okay, so let's see. Theorem 2.3.1. So let xi be independent Bernoulli random variables with parameter pi. So 1 with probability pi, otherwise 0. And then consider the random sum and denote its mean by mu expectation Sn. So this should be, so the expectation of each xi is pi, so this should just be the sum of the pi. Okay, so then the probability that we're greater than t is decaying like this. Okay, so this is like no information for t less than mu. I guess they actually specifically say don't even apply it then, but if t happened to be less than mu, then what would... I guess it would actually still be quite small, because if t... Well, I guess it depends how much t is less than mu, but in the event t is less than mu, we get like some e to the t, but this... Okay, but it doesn't help us in that scenario, because obviously we should expect to be greater than the mean with some like pretty reasonable probability. Okay, so this is what we're targeting, and it looks like our proof is going to use the same method. Okay, so if we want to know the probability that we're greater than t, what can we do? We can multiply both sides by lambda and exponentiate, and then use Markov's. And as exactly as before, we'll get this. Oh, and they even use independence in this step, splitting up the expectation of the exponential sum into the product of the expectation of the exponential. So that's a dependence. Okay, and now we need to bound this. So in the... this is, I guess, sort of like what I was trying to do, or was trying to argue. Oh yeah, I was thinking about that. I think like my argument is maybe sort of overly complicated and it's just Jensen's, but let's see how Verschijnen does it. So yeah, we just need to bound this little bit, and this is a very concrete random variable. It's Bernoulli with parameter pi. Okay, so we have that the expectation of the exponential lambda xi is equal to this, right? So it's equal to 1 with probability, or it's equal to e to the lambda with probability pi, otherwise it's equal to e to the 0, which is 1, so we get this. We factor out the pi, so we get 1 plus this. And then we bound it above by this. Okay, and this is because of this inequality, which is... I guess a pretty classic one. I guess this doesn't constitute a proof, but you just draw this picture and see that the exponential function lies above the line. That's more or less why. So yeah, we have this bound. We just put this this whole thing in the exponent. So we have the exponent of the exponent. Okay, so we have this is less than oh yeah, so we just multiply them all together and we sum up the pi, and the sum of the pi is the mean, so we just get that. And then we substitute into 2.7 and we get this. And then, so this holds for any lambda, and then we choose lambda equals the natural log of t over mu. So it only holds for positive lambda, right? Because if you multiply by a negative lambda, you actually reverse this inequality. And then t over mu is greater than 1 because t is greater than mu. So that's all good. And then if we actually perform the substitution, what do we get? Let's actually perform the substitution. So we'll get e to the minus natural log t over mu t times e to the, so this is now just t over mu. So this is t minus mu over mu. So t minus mu. And then what is this? This is the same thing as mu over t to the t, right, times e to the t minus mu. Wait, this doesn't... Okay, this does become t over mu, and then I combine the denominators and get t minus mu over mu. The mu's cancel, so e to the t minus mu. I thought we were... Oh, right. Okay. And then they just group it up. So they just grouped it up differently. So they then put this e to the t inside there. Okay, so we get e to the minus mu. Oh, I'm doing this behind my picture. So we get e to the minus mu, e mu over t to the t, just as desired. Okay, nice. All right, well, let's see what exercise we got. So we got Chernoff's inequality lower tails, double coffee. Okay, so modify the proof of theorem 2.3.1 to obtain the following bound on the lower tail. For any t less than mu, we have, the probability that we're less than t is less than or equal to e to the minus mu times e to the mu over t to the t. Wait, so it's just the same bound, right? Wait, how is this any different? Okay, well, so where did we use that t was greater than, so where did we use that t was less than mu? I guess we used it when choosing lambda. So if we choose, Oh, okay, so it's just fine. So we just choose a negative lambda in the first step, and then it'll like swap these things around. I guess I can write that up. I think it just works though. Okay. Oh, I'm running out of these guys. Okay, so this is 2.3.2. So choosing lambda equal to the natural log of t over mu, a negative number, because t is less than or equal to slash mu. So what do we have? We have that the probability of Sn being less than or equal to t is equal. So when I multiply by lambda, I reverse the inequality, and then when I exponentiate, I preserve it because the exponential is an increasing function. So this is equal to the probability of the exponential of minus lambda s n being greater than or equal to the exponential of lambda t. Oh, I should get rid of that minus. Lambda's negative, but there's not like another negative. Okay, so it's equal to that, and then we apply, so this being less than that is equal to this, then we can apply Markov's and independence and get this, and then we have like the same thing here, and it, yeah, I guess, yeah, this holds for positive and negative x, so we don't have to worry about whether e to the lambda is, you know, greater than 1 or less than 1. We don't have to worry about that, so I'll just say everything else works. Yeah, and I guess both inequalities, so if you choose mu equals t, then both inequalities are like sort of vacuously true, because these will cancel and get e to the mu, and so you just get 1, but of course the probability is less than 1, so it just doesn't say anything. Well, let's look at the next one. Poisson Tails. Okay, so let x be Poisson distributed with parameter lambda. Then for any t greater than lambda, we have the probability that x is greater than or equal to t is less than or equal to e to the minus lambda times e to the lambda over t to the t. And hint, it says combine Chernov's inequality with Poisson limit theorem. Huh. Let's double check what the Poisson limit theorem is. I think it's just that if you add these things up, you get, wait, it's not, oh, right, this is the page, not the control F. Huh. Okay, so yeah, the Poisson limit theorem is just saying if you add up these unbalanced Bernoulli random variables, that and their maximum is going to 0, so yeah, you need them to be balanced, then you get the Poisson distribution. Let's jump back. Okay, so we need to actually bound the tail. I mean, I'm a little confused why we need like this kind of stuff. I was sort of under the impression that we would like, if we could just like use the definition of the Poisson distribution. So like we've got this for the probability that equals k. Can't we just like say that like the probability that it's greater than or equal to k is like sort of falling off? Let's see if that works. So what is this? This is 2.3.3. Note the probability that z equals k equals e to the minus lambda to the k over k factorial. So this is for z distributed, like the Poisson distribution. I think I'll have to define poise. So I think it should be in commands. Yeah. Just add it there. So let's call it poise. So this is where we are. yeah, like, okay, so the probability that we're greater than or equal to k should be like the sum of this for k equals 1 and so on. And the leading term is lambda to the t over yeah, I'm a little confused why we need like this heavy-duty stuff. It sort of seems like just if we sum this up, it should work out. So yeah, this one pops out, of course, because that's the first term in the Poisson distribution. And then if we, yeah, so we can factor out this and this from each of the following terms to get lambda to the t and t factorial. And then that leaves behind like I guess we should like probably try to understand the hint though and use it that way. Though I kind of think it like sort of just elementarily follows from the Poisson distribution. So does the Poisson limit theorem? I should check if it gives us like a bound. I thought it just gave like the asymptotic thing. So yeah, this goes to this in distribution, but it doesn't tell us whether it is an upper or lower bound, and I feel like we would like need that kind of information. Maybe not. Okay, so if we so I guess this just is the bound from Chernov's, or this is the mean. Oh, okay. So if we okay, yeah, I guess like we don't really need to analyze, but we don't need this. I'll leave it for later. Okay, so we have okay, so let xi equal 1 with probability 1 over n, otherwise 0. Then by Chernov's inequality, we have, now this is key for all n, for all n, we have the probability that Sn is greater than or equal to t is less than or equal to exactly this thing on the right. I don't want it to be 1 over n, I want it to be lambda over n. So therefore Sn, which is just sum, has mean lambda, yeah, slash lambda. Okay. Then by Chernov's inequality, we have for all n that this is going to be less than or equal to, yeah, exactly what we want. Okay, and then as n goes to infinity, the left-hand side, yeah, so as n goes to infinity, the right-hand side is a uniform bound, and the left-hand side goes to the Poisson distribution tail. So by the Poisson limit theorem, the right-hand side goes to, as n goes to infinity, the right-hand side goes to the probability that x Poisson lambda is greater than or equal to t. The left-hand side is a uniform bound, so the limit is bound. All right, that works out pretty nicely. Yeah, I think like you could also like kind of just inspect this and do some algebra and infer that the sum as k goes to infinity is bounded by this. But yeah, obviously this is a little nicer using the Chernoff bound, so that's good. Okay, remark 2.3.4. So note that the Poisson tail bound is quite sharp. Indeed, the probability mass function of Poisson lambda can be approximated via Stirling's approximation as follows. Okay, oh, so yeah, I've already written down the probability equals k, and then, okay, yeah, x. So k factorial is the same as like 2 pi k, so that's where the 2 pi k comes from, the square root of 2 pi k times k over e to the k. So we get the k to the k and the e to the k, and so we get exactly this. And we can see that this is the same as this, except with like k instead of t. So there's just like a polynomial gain. Okay. So, okay, maybe actually that like the algebraic approach where you just kind of manipulate this, manipulate the sum of this wouldn't actually have worked because this is like such a sharp bound. I guess one would have had to be careful. Okay, and it makes kind of sense, like I think intuitively that like the probability of being greater than or equal to k is dominated by the probability of being k for a Poisson distribution, because it's like it's falling off like sort of geometrically. And of course, geometric distributions are summable. So Chernoff's inequality small deviations show that in the setting of theorem 2.3.1 for delta in greater than 0, less than 1, less than equal to 1, that we have that the probability. Okay, so this is like a two-sided bound. So the probability that. So we do need to apply the exercise. Okay, and I guess we stitch them together and we like give something up to make it work for both. Okay, I think I'll stop here and come back at 2.3.5 tomorrow. I was planning on going for about an hour today, and looks like I have. Well, thanks everyone for watching, and I hope you enjoyed it. See you all later.